We're gonna hopefully wrap up here chapter 2, what's left of it. We were obviously spent a lot of time last time talking about electron configuration. So that is the order at which electrons do go into the atom. We do write it based on sort of filling order, and what's sometimes referred to as the off-ball principle is the idea that protons are basically added to the nucleus one at a time. And that's sort of how electrons go into the atom as well. We do start with obviously the lowest energy level and then kind of fill it up as we talked about several sort of rules as to how they sort of populate the orbitals. The first one is, it sort of goes in sort of the upward direction with a positive half spin first quantum number. Second one in a particular orbital does come in paired, so opposite spins in the same orbital. One of the main reasons for that, as we talked about, is what is known as Paulie's exclusion rule, which basically states that no two electrons that are basically in the same orbital could have the same 4 quantum numbers. So basically, if you kind of put, for example, the arrows in theory, upwards or downwards together, they will end up with the exact same 4 quantum numbers. The way we sort of get around that is, for example, here on the 1s orbital, we throw an electron that goes in the upwards direction and the guy here going in the downward direction. And that allows them to really have different quantum numbers. We do end up, for example, here n would equal 1, L would equal 0, M sub L would be 0, and the MS sub S would be plus a half. For this electron, almost identical in terms of this quantum numbers, but what allows it, again, not to violate sort of Pauli's exclusion rule is it is spinning in the opposite direction that has a spin quantum number of minus a half. And again, this sort of arrangement is what is referred to as the spins being paired with each other, basically opposite spins there within the orbital. We also talked about sort of Hund's rule. Hund's rule is the idea that really the kind of stablest situation or the best situation for electrons is sort of to maximize the parallel spins. And that comes into play, for example, when we got something like some p orbitals here. And we could, when we start filling electrons, just pair them off, but that would not maximize the parallel spin. So we really don't do that. So when the second electron comes into a set of p subshell, we do sort of fill in each orbital basically with one electron before we come back and start pairing them off. That again maximizes that sort of parallel spin and sort of helps out the stability of an atom in terms of its electrons. Obviously, at this point, we would come back and start pairing it off, but that still is maximizing the sort of parallel spins that we would have in that sense instead of just pairing them off right up off the bat. And that's what's referred to as a sort of Hund's rule. We obviously did our orbital diagrams and stuff like that we saw here. Any questions on any of that stuff there? Electron configuration, orbital diagrams, all that kind of stuff. Okay. We also talked about things with charges, right? So remember that if something does have a charge, you do need to adjust the electron configuration for it. If it's a representative element, a sort of left-hand side, right-hand side of the periodic table, those guys, if they lose or gain electrons, typically will end up at group number 8, the periodic table, which is the noble gases in terms of their electron configuration. Transition metals are a little bit different. When they do lose electrons, as we talked about, they will lose again their sort of s electrons first, as they end up actually being higher in energy than the d orbitals. And those sort of highest in energy electrons are what are referred to as the valence electrons. Valence electrons are really important, especially what we're talking about in the next chapter, which is with bonding. They're the highest energy electrons. They're found furthest away from the nucleus, and again are really the ones that sort of come in contact with each other when different elements come together and are participate in bonding. So if we look at the electron configuration here, there are basically these 8 electrons on the second energy level, which would be the higher than these guys here. So this guy here would have our 8 valence electrons. Again, the lower energy electrons are sometimes referred to as core electrons. Again, really, those are not involved in bonding or anything like that. They're really too close to the nucleus to sort of escape, if you will. They're basically feeling the full effect of that positive charge on the nucleus. So there's a couple different ways that you can sort of figure out the valence electrons. You could simply write the electron configuration, and go, okay, these are the highest electrons there, and this guy would have 2 valence electrons. You also can just look at the group number. So on the periodic table, the group number is equal to the number of valence electrons. And group numbers there up on top. So for example, if we look at something like sodium, which is group 1, is configuration 1s2, 2s2, 2p6, 3s1. That would be its 1 valence electron there. If we went next door to magnesium, 1s2, 2s2, 2p6, 3s2, that would be its 2 valence electrons. So the much quicker way is just to go look at the group number on the periodic table equals the number of valence electrons that there are. For transition metals, it's a little bit different, and good thing is we don't get too far into anything dealing with valence electrons and transition metals, since transition metals really do lose those s electrons from group 1 and 2 first. A lot of people consider them to have sort of 2 valence electrons, but because they could then lose their d electrons next, they could have upwards of sort of 12 valence electrons, although nothing would ever probably lose 12 electrons and become like a plus 12 charge or anything like that. But they do have the potential, obviously, to dig into the d orbitals and those electrons like we talked about when we were doing transition metals and losing electrons. So a lot of people will roll with 2 for these, which is the 2 sort of s electrons. But I have seen people say, hey, they could have upwards of, sort of 10 or to 12 because of those d orbitals can be in use as well. Any questions on valence electrons there? Obviously, this is what we did last time in terms of electron configuration. Obviously, this is probably the better move as we talked about in terms of writing the order. You could also, as we talked about, sort of count it off on the periodic table. You just want to remember a couple of things like we talked about last time. Again, the main thing is the D starts here, which is 1 behind the period number. So that's 3D. And really these guys down here, that's 4F, which is 2 behind the period number there for our F electrons. All right. So we did some electron configuration last time. So we'll just kind of skip through these guys here. And we talked about our transition metals, and we also talked about some of the exceptions that there are. Again, there's a lot of exceptions to the normal electron configuration there in the transition metal region, especially if you go below copper and chromium, like we talked about on the periodic table. There's some, again, like PD that has like all the electrons from the S sort of have went up to the D orbitals. The 2 that we talked about that you are responsible for is chromium and copper. Again, you should be aware underneath those guys like silver and stuff like that, there's a lot of exceptions, but you don't have to worry about remembering those. So we'll just do the chromium and copper are the 2 that you need to. Remember that the main exception or difference is that basically for both of those, they have only 1 electron in the S, and basically that other electron has moved up to the D orbitals. And again, just been found experimentally to be really stable. And again, those guys are super close in energy to begin with, so it's not that hard for sort of that electron to make that transition upwards as well. All right. And here's our list of some of the exceptions that we talked about. All right, so now that we talked about sort of the electron configuration, let's then officially talk about the periodic table. That is the periodic table. It is nice. All right, So let's talk about some of the parts of the periodic table. First off, a group, or if you're really old like me, family. Not too many people call it family anymore. Most people call it groups. And groups are basically columns on the periodic table, up and down. We use the representative numbering for our groups, and that is usually sometimes referred to as the A numbering. If you look on some periodic tables, you'll see some numberings are A, some numberings are B, and then some are just sort of numbers. A numbering is basically right here. Group number 1 is there. It actually starts with lithium. It does not start with hydrogen, even though on every periodic table you will find hydrogen there. We'll talk about why that is in a second. Right next door is group number 2. Then we kind of skip the middle part, and over here is group 3, group 4, group 5, group 6, group 7, and group 8 over here. So they're basically group 1A, 2A, 3A, but most people don't put the A in it. They just call it group 1, 2, 3, 4, 5, 6, 7, 8. And that's the number pretty much that you use in every chemistry class you come about. As you can see on this one, again, there is some B numbering, and then it's just some straight 1 through 18 numbering as well. But we definitely use that A numbering here. Each horizontal row is a period, and there are 7 periods on the periodic table. Helps us with electron configuration, like we talked about. Again, periods heading in this direction from left to right on the periodic table. The number that we see up on top of the element, as we talked about in an earlier chapter, that is the atomic number. And once again, the atomic number is the number of protons that you find in that particular atom. A reminder as well that the bottom number that you see is not the mass number, but it is what is known as the atomic mass. Any questions on that there? Now, the periodic table really is broken up into sort of 3 categories. We have metals, we have non-metals, and we have what are sometimes referred to as metalloids or semi-metals. On most periodic tables, as you can see here, there usually is sort of like a staircase that kind of comes down right about here. And that staircase, pretty much to the left of the staircase, and not pictured here, but also those 2 guys that are on the bottom, those 2 rows are on the very, very bottom by themselves. Those are all metals. Metals are really good conductors of heat and electricity. They are also malleable. You can pull them into wires. They typically have very shiny appearances. Pretty much most metals are solid at room temperature. Pretty much the only one that is not is mercury. So mercury is our only sort of liquid there, metal at room temperature. Kind of up to the right here of that staircase are where we find our nonmetals. And nonmetals pretty much have the opposite characteristics of metals. They are bad conductors of heat and electricity. They're dull, they're brittle. But also very different is a lot of nonmetals have different sort of states as they come. A lot of them are gases. So a lot of those sort of nonmetals like hydrogen, nitrogen, oxygen, chlorine, fluorine, these guys are gases. They're also those diatomic molecules that how they naturally come by themselves. Something like bromine is a liquid with a little bit of vapor over it. And things like carbon and sulfur are solid. So a lot more variety in terms of the states, in terms of how they come. And that is why over here for group number 1, this guy is not part of it. This guy is hydrogen. Hydrogen is a non-metal. Yeah, so hydrogen is actually a non-metal, even though it's hanging out over there in group 1. And that is why it's not part of group 1, even though on most periodic tables you will see hydrogen over there because it has some special properties, kind of behaves a little bit like a metal in some cases, but it really is a non-metal. Years ago on periodic tables, they used to throw hydrogen on both sides. You'd actually see it on both sides, but not too many periodic tables do that anymore. But again, hydrogen here a non-metal, not a metal. And again, that's why group 1 does start with lithium, which is right below it. Right there, sort of in the middle of the two, is our staircase, and that is our semi-metals, or sometimes referred to as metalloids, just to overlay it here. Some books will include boron in that, which is right there, and that's sort of a staircase that comes down. Metalloids are semi-metals, as they're sometimes referred to, basically have properties that fall really on both sides, and that kind of makes sense based on their location. They're kind of in the middle there of our metals and our non-metals. So the same semi-metal can have some properties that are very similar to what we see in metals, and the same guy will have some properties that are very similar to what we see sort of in non-metals. So semiconductors and those type of things are what you kind of find in that region. As they kind of fall on both sides of it. Any questions on that there? Now, there are some groups that have special names. So starting with group 1, which once again does start with lithium, that is the alkali metals. Over here in group number 2 is our alkaline earth metals. Alkaline means basic, and that is where we find a lot of our bases come from, things like sodium hydroxide, potassium hydroxide, calcium hydroxide. So pretty much if you throw a hydroxide on anybody there in group 1 or 2, you will get a basic solution, pretty much like what you did yesterday when you took the piece of calcium metal, threw some water in it, right? You should have saw your litmus paper turn blue at that point afterwards, and that means it's basic. You basically made a base, and that's pretty much what happens, like I said, when you mix basically water with anybody kind of there in group 1 and 2. And that's really where a lot of those strong bases actually do come from. Once again, here we're going to skip the middle part, come to the other side here, and that is group 7 right here. And that is the halogens. And that is also those guys that we played with yesterday there that I did in part 3 of the experiment. That's our fluorine or chlorine or bromine or iodine. Those are our diatomic guys. They come as 2s normally by themselves. And as we saw, right, reactivity increased as we went up that group there in group 7. Right next door is the last sort of group that you need to know, sort of a special name, which is group number 8, and those are our noble gases. Noble gases are pretty much what are referred to as being chemically inert. They're unreactive. They'll react with themselves, but pretty much nobody else. And they're really, really stable. And as we talked a little bit about, and as we'll talk definitely more in bonding chapter coming up, that is pretty much the goal of everybody, is to get to the same sort of electron configuration as that group 8, so they can be very, very stable like those guys are. There's also some noble gases, things, I'm sorry, noble metals like gold is a noble metal and so forth like that, which is very unreactive with a lot of things. 2 rows on the bottom technically are put there so your periodic table isn't 40 feet wide. But if we do follow the numbering, this is 56, and that is 57, and then that is 72, so that is 58. So technically, these 2 rows here should go right about here in that spot, and that's 89 and 104. So those 2 guys technically should be slapped right into there. They're called the lanthanides and actinides because those are kind of the elements that they sort of follow on the periodic table. The good news is we don't really deal too much with it. A lot of our radioactive guys are there on the very bottom. A lot of sort of the man-made elements like Einsteinium, californium, all those kind of things, which are really radioactive type elements, are found there on the bottom of the periodic table. I will say sometimes, depending on the periodic table and when it was built, this part of the periodic table may vary very greatly. That's sometimes where they throw in elements. They haven't decided if they're going to make them elements or not. And that's why you can see on that periodic table over there, there's a lot of kind of almost like outline elements in that sort of area. Again, sometimes depending on when it's made, you may find some different sort of symbols in that area and stuff like that. Any questions on that there? One last important area, obviously, is between group number 2 and group number 3. These are our transition metals that are basically in blue here. So all these guys are our transition metals. Transition metals are metals that basically have sort of a variable charge in most cases. They can make multiple types of charges. Something like iron could be iron 2, iron 3. Copper could be +1, +2 in that situation. Now, this is also why these bottom two rows here, that technically does go in here, these bottom two rows are sometimes referred to as inner transition metals, because frankly, they should be right there in that sort of transition metal region. I've only seen one periodic table ever that put them in the right location, and it was on a wall, and it took up the whole wall because it just pushed everything all the way over to the right and stuff like that. So any questions on sort of the periodic table? You need to know, obviously, which way groups go, yes, which way periods are. You need to know the correct representative numbering of 1, 2, 3, 4, 5, 6, 7, 8 in terms of the groups. You need to know the special names, that group 1 is the alkali metals, group 2 is the alkaline earth metals, where the halogens are, and which group are the noble gases. You obviously need to also know metals, non-metals, and metalloids, where they can be found and some of their properties. And I think that, and obviously transition metals as well. Any questions on any of that stuff there? Okay. All right, so what we're going to finish up here, since talking about the periodic table, is we're going to talk about some periodic trends and why certain things sort of occur, or why we see certain things with metals and non-metals. Talk about a few different types of periodic trends here. We're going to talk about ionization energy. We're also going to talk about electron affinity. We'll talk about the atomic radius, and we'll also add to this list, which is really out of chapter 3. The only thing from chapter 3 that you'll need to know for the first exam is what is known as electronegativity. So we're going to talk about each of these and sort of their trend on the periodic table. So let us talk about then ionization energy first here, and let's kind of talk about what that is. So ionization energy is the energy required to remove an electron from the gas phase of an atom. So the ionization energy is that energy you need to put in there basically to pop off an electron. By the way, electrons are lost basically one at a time. So they don't all just pop off at once. It's kind of like how they're added to the atom one at a time. They're sort of removed one at a time. So if we took something like magnesium, like what we see here, the first thing that would happen is the magnesium that has no charge would basically lose one electron. So that's why we see the electron on the right-hand side like it's being given off, and become a +1 charge. The energy associated with removing that first electron is sometimes referred to as the first ionization energy, and it takes about 735 kilojoules. The next thing that would happen is that guy that now has a +1 charge will then lose a second electron. That's going to make it now have a +2 charge. And the energy required to do that is what is referred to as the second ionization energy. What would happen perhaps after that is the guy now with a +2 charge would dump off a third electron here and then become a +3 charge. That is what is referred to as the third ionization energy. And if we write again our electron configuration here for magnesium 12, there we go, 3s2. When we look at this, first off, a couple of things we should see. What happens in terms of the energy as we go from removing the first electron to the second electron to the third electron? Is it easier to remove the first electron, or is it harder to remove the first electron than the second electron? Which one is the easier one to remove? The first one is easier. It only takes about 735 kilojoules of energy to remove that electron. What happens when we remove the electron in terms of the overall sort of size of the atom? Does it get smaller or does it get larger? It gets smaller, right? You remove an electron, it's part of the electron cloud shrinks, right? And that means that those electrons that were a little bit further away from the nucleus to start with have now moved themselves closer to the nucleus, right? That means that they're going to be held stronger or not as strong. Yeah, they're going to be held a little bit stronger. So it's going to take more energy now to remove the second electron. And that's what we see here, right? We go from 735 to about 1400. So you need twice the energy there in this case almost to remove that second electron because everything sort of collapsed in on itself a little bit in terms of its electron clouds. Now, when you do obviously the second electron, we're going to get even more of everybody moving in closer. And it takes almost now 7 times the amount of energy to try to pop off that third electron for something like magnesium. And it frankly does not happen. And it does not happen for a couple of reasons. How many valence electrons does magnesium have? It has 2, which are these. We could get it from the electron configuration or look on the periodic table and see that magnesium is group number 2. So after we get rid of the 2 valence electrons, we are now dealing with our core electrons, which were from the beginning super close to the nucleus. So they're even closer now, and it really doesn't happen at that point. And that's why we know magnesium here actually will only go to a +2 charge, and it will not really do this under normal conditions because that is now delving into those core electrons, which takes an enormous amount of energy to try to rip them out, and it just really doesn't happen under normal cases. So that's why something like magnesium, which is group number 2, will always have sort of a fixed charge of +2 because it sort of gets into that core electrons, and it just doesn't happen. Any questions on that there? Now, in general, when we look at the general trend for ionization energy on the periodic table, the general trend is as we go up and to the right, the ionization energy increases. And as we go to the left and down, the ionization energy decreases. So on the periodic table in general, ionization energy increases up and to the right and will decrease as you go left and down for a couple of reasons. First off, as we go up and to the right, as we'll talk about, we have a lot more protons happening there, which means our nucleus has a much stronger positive charge, is going to bring everybody in closer. So the overall size of the molecules or atoms on the up and to the right are much smaller, which means those electrons are closer to the nucleus to begin with, going to take a lot more energy to try to remove an electron. As opposed to the left, we have a little bit less of protons there, not as big as a positive charge, and not going to be holding those electrons as tight as what you see on the other side. So again, electrons added in the same principal quantum number do not completely shield the increased nuclear charge caused by the added protons. Electrons in the same principal quantum level are generally more strongly bound from left to right. There's one thing that was referred to also as was referred to as effective nuclear charge, sometimes referred to as Z effective. And that's sort of the charge that electrons feel within an atom. So for example, if we looked at something like lithium, which is 1s2, 2s1. When we look at this guy, we basically have a +3 charge there for our nucleus. We have basically 2 electrons in the n equals 1 level. And then we have basically in the second level a valence electron, right? Lithium is group number 1, so it has 1 valence electron. When we think about these core electrons, which are these guys here, they're pretty much, right on top of that +3 charge. So they're feeling really the full brunt of that +3 attraction. One important sort of idea between like things that are positive and negative when they are attracted to each other, as sort of the charge increases, so something with like a +3 and -3 are much more attracted to each other than say something with a +1 and -1. So there's a lot stronger of attraction when the sort of overall charge is sort of large on both sides. When we get to this electron, that third electron, which is our valence electron out over here, he experiences what we sometimes refer to as shielding. And what happens with that valence electron that's on the outside there is, frankly, he is not feeling the full brunt of that positive charge on the nucleus because he's got those lower energy electrons sort of in the way. Kind of like when you go to the movie and you sit down like a nice perfect seat in the center, and then somebody comes in like with a big cowboy hat right in front of you, sort of shields some of the screen, right? You're not seeing the full effect of it. And that's sort of what happens here. You can actually calculate Z effective by taking the positive charge on the nucleus and how many electrons are shielding. And that tells us that actually this valence electron out there is actually feeling more like a +1 attraction to that nucleus rather than the full +3 attraction to the nucleus. And that means it's not going to be held as tightly. And that is why something like lithium, you don't need a lot of energy to remove that electron. It's not going to be held as tightly. Z effective increases as you go to the right. Again, more protons, going to have a little higher of an attractive force to begin with. And again, that's why it takes a little bit more energy as you go up and to the right there on the periodic table to remove an electron. Any questions on that there? So here's a little graph of the ionization energy for the elements in the first 6 periods. And the general trend that we see, again, is what we talked about to the right on the periodic table. We're going to see an increase in that ionization energy, and coming down a group, and to the left there we will see a decrease. So much easier to remove electrons for guys on the left hand side of the periodic table than on the right hand side of the periodic table. So the graph that we just saw for ionization energy versus atomic number is not linear. Again, we are talking about electrons that are near each other. So just by that definition, they don't want to be hanging out near each other. So we have a lot of electron repulsions that are happening. And obviously there's some exceptions that we see in that trends. All right, so which atom would require more energy to remove an electron? Would it be sodium or chlorine? Which one here? So if we look at the periodic table, sodium is here, chlorine's over here, and they are both in the same period. So once again, ionization energy should increase as we go to the right on the periodic table. That means that we should expect chlorine to have more energy needed to remove an electron in this particular case. If something has a very high ionization energy, would they typically want to give away their electrons? No, right? It's very hard to do that, right? If you have a low ionization energy, then obviously it's a lot easier to do so. Which atom would require more energy to remove an electron? This is lithium and cesium in this case. These are two that are in the same group. That means that ionization energy will actually decrease as we come down the group. And that means in this case, it would require lithium more energy to remove that electron than cesium in this case. Which has a larger second ionization energy, and why? So that is lithium and beryllium in this case. So we have lithium, which is 1s2, 2s1. We have beryllium, which is right next door at 1s2, 2s2. Now, in this particular case, the answer is which one? It is lithium in this case. Right? So you may be saying, but isn't lithium to the left, right? It is, but here we are actually talking about the second ionization energy, which is meaning that it's going to lose 2 electrons, right? Lithium is group 1, which typically will make a +1 charge, and that is because with lithium, that has 1 valence electron. Now, to get to the second ionization energy, we are now digging into core electrons here, right? Which, as we saw in that chart, will take a lot more energy to do so. Beryllium, which is group 2, actually has 2 valence electrons, which means when it goes to take off the second electron, we're still dealing with those valence electrons, and it shouldn't take as much energy as to try to rip off a core electron out of lithium. So that is why here lithium should have the higher second ionization energy. Any questions on that there? So here's a table of some of the ionization energies. And once again here, sodium typically makes a +1 charge. And after that, we are delving into our core electrons. You can see a tremendous jump, a 10-fold jump in energy. There's our magnesium, as we saw on that one slide. Again, big jump into our core electrons and so forth. But the general trend that we do see, as we talked about, is, again, first ionization energy usually lowest, second gets higher, third gets higher. Again, it gets progressively harder to continuously try to remove those electrons as the overall size starts to shrink and those electrons find themselves closer to that positive charge. Aluminum could get up to 3 before you can see a super big jump in energy if you try to pull off that fourth electron in the case of aluminum. Any questions on ionization energy? Ionization energy is what we do to remove an electron. So when we think about ionization energy, as we just talked about, we typically associate it with losing electrons, which means we associate it with cations, right? Which are guys that will lose electrons, become positively charged. Electron affinity, on the other hand, is the energy change associated when an atom basically will accept an electron. So electron affinity is that energy change that occurs when somebody accepts an electron. That's why we see the electron on the reactant side here. So when somebody accepts an electron, they become negatively charged, and we usually associate electron affinity with the formation of anions, which are negatively charged ions, and getting those electrons. In terms of its trend, it has a similar trend. It will increase as you go up and to the right on the periodic table. It will decrease as you go left and down on the periodic table. So typically our guys up and to the right have a very high electron affinity, and they like electrons basically, right? If you have an affinity, you sort of like something. It's not a perfect trend, it's the general trend. There is some differences. For example, if you look at the halogens, actually chlorine has a higher energy change than fluorine. So there's some differences, but the overall trend is up to the right, it increases, left and down, it decreases. Now, this relates to sort of the size. When we talk about the overall size of an atom, as we go up and to the right, it gets much smaller. So size decreases as you go this way and will increase as you come this way. Again, to the right on the periodic table there, you're going to have a lot more protons. Again, going to create a larger positive charge and going to bring everybody in to start with a lot closer to the nucleus than to the left, which will have a little bit lower of a positive charge and won't pull everybody in as much, and also would have less protons and less electrons as well as you head to the left on there. So the effective nuclear charge increases, as I mentioned before, as you go to the right because of the larger protons that are there. So even those sort of further ones, electrons on the right-hand side and up on the periodic table, even though they're being shielded because of that larger positive charge of the nucleus, they effectively get a larger effective nuclear charge. So even though they're not feeling the full brunt of it, because there's so many protons, it's still enough to bring them in more than what you would see on the left-hand side of the periodic table. Any questions on that there? And that's what we see here. And again, you can see up and to the right, much smaller, down and to the left there, a little bit larger in terms of its size. So let's talk a little bit about some of these trends, and one as well, which is, go back here. All right, so let's talk a little bit about electronegativity to add to our little list here. Electronegativity, which again is different than electron affinity. Electronegativity is the ability of an atom to bring electrons towards itself. And in general, on the periodic table, it increases as you go up and to the right, with actually fluorine being the most electronegative element you could have. And it decreases as you go down on the periodic table. So as you go up and to the right, they have the ability to really bring electrons towards themselves. As you go left and down, pretty much they really don't want to bring electrons towards themselves. So electron affinity is the energy change that occurs as a result of gaining electrons. Electronegativity is the ability to really bring those electrons towards itself. So if we sort of put together all of our trends here that we just talked about on the periodic table, we sort of see, why certain things occur. So first off, going from up and to the right, the size decreases. And coming this way, the size increases. Going from left to right there, our ionization energy increases and decreases as you go down. Our electron affinity increases as you go up and to the right and decreases as you come down. And our electronegativity increases as you go this way and decreases as you come that way. So for the most part, what we find for our nonmetals, which as we just talked about here, can be found over here, nonmetals, right? Up and to the right on the periodic table is where you find your nonmetals. These are things that are very small, which means their electrons to begin with are very close to the nucleus, and they're going to be held a lot tighter. It takes a tremendous amount of energy to try to remove electrons because they have very high ionization energy, and they have very strong electronegativity, which means they actually want electrons. So typically what happens with our nonmetals is they typically will gain electrons because of all those properties. They're going to bring electrons towards themselves. They're going to hang on to their own electrons, and that's going to allow them to gain electrons. And that's why nonmetals typically will become anions, right, which are negatively charged because of all these trends. On the other side of the periodic table, heading towards our metal side, really, which is over here, our metals. These are guys that are much larger, which means their outer electrons are not being held as tightly. You don't have to put a lot of energy in there to have them remove their electrons. And frankly, they have very low electron affinity and electronegativity, which means they're not really interested in gaining electrons or holding on to their own electrons. So these are the guys that typically will lose electrons and become positively charged cations. Any question on any of those sort of trends there? And that is why when you put together a metal and a nonmetal together, you get an ionic compound, because the nonmetal's like, I want your electrons. The metal's like, I don't really care. Go ahead and take them. And that is what happens in that case. You get the transfer of electrons from the metal to the nonmetal, and you get basically an ionic compound, because now the metal is positively charged, the nonmetal is negatively charged, and it's that electrostatic attraction that comes together and basically holds that unit together. There's absolutely no sharing of electrons. That is also why when you have a covalently bonded guy where we're sharing electrons, that typically occurs when we get two nonmetals together, because both of those guys are like, I want my electrons and I want yours. I want your electrons and I want yours. So best that they could do is decide we'll just share electrons rather than somebody lose electrons. So that's why when we get covalent bonding, as we'll talk about in the next chapter, when two nonmetals get together, the best they could sort of agree upon is we'll just share. That way nobody loses their electrons and they both can kind of hang on to them. And that's, again, different than the ionic bond where basically one's giving it up and one is accepting its electrons. Any questions on that there? All right, so let's see here. All right, so which should be the larger atom, sodium or chlorine? So again, they're in the same period. We see sodium further to the left, again, with all those properties of less protons, right? Lower ionization energy and all that should probably be our sodium in this case, should be the larger. Lithium and cesium, in this case, they're in the same group, and we see cesium is further down, which means it should actually be the larger atom in that case. Also has obviously more electrons, right? Bigger electron cloud because of that, to go with his larger protons. So which is larger? Is it the hydrogen 1s orbital, the lithium 1s orbital? And which is lower in energy? Is it the hydrogen 1s orbital or the lithium 1s orbital? So take a second, think about each of those, think which one is right in each of those cases. Okay, so let's take a look here and see. We have the hydrogen 1s orbital is larger, again, is further up on the periodic table. We're comparing 1s orbital to a 1s orbital in this case. Also, hydrogen only has one proton, right? So not gonna kind of pull it in as much as opposed to our lithium there that has actually 3 protons. And that is why the lithium 1s orbital is lower in energy, because hydrogen has the +1, which is going to bring in our s orbital, but lithium here has a +3 charge in the nucleus, which is going to pull that orbital in closer. Again, the larger sort of the positive negative sort of charges, the stronger the attraction. So that's going to pull it closer into the nucleus and would result in this 1s orbital being actually lower in energy than what we would see in the hydrogen 1s orbital. Any questions on that there? Lastly, we want to arrange these elements, oxygen, fluorine, and sulfur according to increasing ionization energy, which obviously it did for us. So I guess we'll go through it here. So we have oxygen, fluorine, and sulfur. So on the periodic table, it looks something like this: sulfur, oxygen right above it, and to the right there is fluorine. So in terms of ionization energy, remember ionization energy increases as you go up and to the right, it increases. So we should see increasing. So sulfur would be the lowest ionization energy, to fluorine, which would be the highest. In terms of size, size also decreases as you go up and to the right. So in this case, the smallest guy would actually be sulfur, so fluorine, and the larger guy would be sulfur in that case. Any questions on any of those there? All right, a couple of final thoughts here on the periodic table. As we talked about, the number of valence electrons is primarily determined by the atom's chemistry. It's also, again, equal to the group number. We can count off electron configuration like we saw there from the periodic table. by using the period and basically the S block, the P block, the D block, and the F block. And obviously they do have some special names as we come through here in our periodic table. The basic division obviously is into our metals, non-metals, and metalloids, as we talked about. It looks like maybe they may not include boron there in your book as a metalloid and our alkali metals. I did want to take a second here to talk about, since we've been talking about things with charges and ions, which obviously are ions. There are certain things on the periodic table which have sort of fixed charges, and that's a good thing to know as we go into the next chapter, which is bonding. So basically everybody in group 1 will be a +1 charge. So they have fixed charge. So that's, again, starting with lithium, sodium, potassium. Everybody here in group number 2 will have a +2 charge. When we come over here to group 3, and we're really talking about aluminum for the most part there, we'll have a +3 charge. There's no good pattern here in 4, but talking about the non-metals going into group 5, these guys will be -3. Right there in group 6 will form -2, and group 7 will form -1. So these are sort of fixed charges, and I got, again here, as we've been talking about, the metals here will be positively charged, so +1, +2, +3 to aluminum. Skip 4, -3, -2, -1 for our non-metals to come here. Our transition metals typically can have a variable type charge, so most of those guys could be, you know, like I said, +2, +3, +1, +2. Even some of these guys down here, sort of in this region, which typically are not transition metals, but where you find things like lead and tin and things like that, they also can have variable type charges that occur. And remember that we do have the staircase coming through here. And, you know, kind of above the staircase is non-metals in some of these groups, but below the staircase are still metals. So you have positive and negative guys in the same group on the periodic table, with obviously our staircase coming through here. There are a few non-metals that, I'm sorry, there are a few transition metals that, even though they're transition metals, they also have fixed charges. And that's sort of this backwards L here, that's zinc, cadmium, and hang a left there to silver. So zinc and cadmium, even though they're transition metals, they also have a fixed charge. They will always be +2 when they make a charge. And silver also has a fixed charge of +1. So silver will always be +1. Other than that, everybody else sort of in the transition metal region and a little bit to the right of it there has the ability to sort of make multiple types of charges. So really everybody else, you know, sort of in this region here, and then a little bit outside of that, has the ability to make the variable type of charges. Any questions on that there? Okay.
Is that because for silver, when it forms a +1 charge, one of the S electrons goes down to the orbital completed?
Yeah, so exactly. So some of it has to do with, again, silver does have that sort of exception in electron configuration where the electrons are and stuff like that, and some of these other ones, but silver definitely does. But it has a little bit to do that. There's just certain, because of that, sort of the valence electron, you know, is sort of the only one that will be lost in that case. Always will just be that one that's lost from the S. Yeah. Other questions? Okay, so I think that should wrap up this chapter here. We talked about group 1, I think. Enough. All right, that should wrap chapter 2.